Good evening, ladies and gentlemen. While the people are still straggling in, I'm going to get started because we have a full program here. So let me introduce you to Anthony Milian. He's a system engineer at the Weapons Systems Engineering Group at JHU APL and Missile Defense Sector. He has 3 years of experience conducting system-level performance analysis of missile defense systems, currently completing a PhD in systems engineering in Colorado State University with research focused on model-based system engineering and system architecting. He also completed an MS in system engineering from Johns Hopkins in 2018 and is an INCOSE Associate System Engineering Professional. He's going to talk to us about the methodology tailoring for development time optimization. Basically, the research is tailored for ISO, IEC, IEEE 15288 technical processes to incorporate the meta design flow and extend it to end-to-end systems engineering methodology. The resulting methodology facilitates applying meta design flow to different domains such as healthcare and product line architectures. I can tell you the potential application of the methodology for optimizing operating room design presented at the 2018 INCOSE Systems Engineering in Healthcare Conference will be discussed in detail. Thank you. Without much ado, here is Anthony.
Thank you. So, as I said, I'm Anthony Milian. I work here at APL. I actually recently transitioned to the force projection sector here at APL. I'm working for the KBH group. And I'll be talking about methodology tailoring for development time optimization. It's the topic of my research in my master's thesis at Johns Hopkins University and my follow-up research in my PhD at Colorado State University. So let's get started. So I'll be talking about 3 main areas here. First, I will give you a little bit of a background. Hopefully, the background portion will feel like a little bit of a story that I want to tell about how this research came to be and what the real problem that I personally addressed through my research is, which can, hopefully you see, can draw a little bit of confusion, but I hope to set that straight. And then I will talk about my actual research and what the results of the research were. And I will talk about additional efforts such as the INCOSE Systems Engineering in Healthcare presentation, which was a specific potential application of my research that I presented, and my follow-up research through my PhD. So, before we get started, this is systems engineering, right? So I feel like it's completely necessary to go ahead and get started with a few definitions. And I'm not claiming that these are the most correct definitions for these terms in the field, but these are the definitions that I settled on for my research in order to get everyone on the same page when I start talking about terms that may mean something to you in your field and something different for someone else. So first of all, model-based systems engineering, or MBSE, for those who are not familiar with it, is basically an approach, a systems engineering approach that focuses on using descriptive models as tools to support system development and definition and all decisions in the system development process. Now, the system development life cycle, think about that as the stages of system development from concept development through design, operation, and eventually disposal. So it's that time component of system development. Now, design flow, specifically in the context that DARPA was using, and you will see relative to my research, is a portion of that system development life cycle that specifically addresses system architecture and design. So design flow is a piece of SDLC, right? And then we get methodology, process, and activity, and I'll go backwards on those. So activities is what systems engineers do, actual things to do, like requirements analysis, that's an activity, that's something you go do. You define the architecture, those things. And then the processes contain those activities. So a process is made up of activities and it transforms inputs into outputs. And then the methodologies, that's the systems engineering guidance on which processes to do in which order. So methodologies are made up of processes, and processes are made up of activities. And that's very easy. Those are the terms I will be using throughout this presentation. So let's get started talking about what the real challenge is that was being faced and it's system complexity. And let's remember, as systems engineers that we are, that the value of systems engineering as a technical field is that it's historically been able to manage complexity. But, you can read that as complexity and change continue to escalate in our products, in our services, in our society, then reducing the risk associated with process development and system development is the job of the systems engineer. So that's what defines the job of a systems engineer. However, even today, even with the long history of systems engineering, there are modern challenges related to complexity that systems engineering professionals face. And some of these challenges are expressed in INCOSE documentation. Things like mission complexity growing faster than our ability to manage it is a big challenge. And another one is that the systems engineering are forming pieces, focusing on the pieces rather than the architecture, and optimizing the design of the pieces instead of focusing on the big picture. So those are things that are still challenges that we face in the systems engineering community. More specifically, there was a focus by DARPA on military system complexity, and they made this study right here, which was focused on comparing military system development exemplified through the aerospace industry, and how, as complexity continued to increase through the years, and that's the x-axis over there, the development time would continue to increase, and that's the blue line you see right there, that's the aerospace industry, so building an aircraft, a military aircraft. But compare that to other industries. They were saying integrated circuits and the automotive industry. As complexity has equally continued to increase, they have been more able to adapt with that increase, and their development times have not continued to increase as drastically, and DARPA didn't like that, and who would, right? And they were proposing that line over there and see, well, in the future, when complexity increases even beyond what we have today, and it matches what other systems have been able to do, how can we go back and fix this trend and go back to lower levels of development time? And that's where we're getting into the development time optimization, right? And they identified that at least part of the problem with this was systems engineering, and now they're blaming us, right, INCOSE. So they were pointing out some specific shortcomings in the way that systems engineering was applied specifically to military system development. So they weren't saying that everything in systems engineering was wrong. They were just saying that there were a few things that were wrong. And first of all, they were started talking about functional decomposition and the very famous stovepipes that are created, right? You decompose your system and you create stovepipes. And then you would start optimizing at the component level based on size, weight, and power, while your high-level architecture is optimized for cost, and then there's an inconsistency in the optimization goals. They were talking about this whole structure of stovepipes was disincentivizing the abstraction of your design and was limiting integrated solutions from being developed, because the people who were at the lower level focusing on one component didn't even care about the system level solution. They would focus only on their component. Then once you got down all of that and you started integrating, after you had optimized everything individually for size, weight, and power at the component level, and you started to integrate, you only simply had what they call a brittle point solution, point design solution, which is like your architecture only does one thing, and that's what your requirement said that it has to do, because you optimized every component to do that one thing that your requirement said. And by doing that, you end up with those old tangled architectures over there where everything tries to come together, and you end up with emergent behaviors. Your system starts doing things that you could not have predicted because all of your interfaces and the sheer number of interfaces that are in your system, because you optimize everything to do their own thing by itself to support the system, but not focusing on minimizing the number of interfaces, then you end up with that mess over there of all of your interfaces. And once you went into testing, you would find out that your test failed, and you didn't even know that your system would show up with this behavior that was never planned and never identified. And finally, they were finding that traditional V&V methods, verification and validation, they did not scale properly with complexity. Specifically, once the number of system states reaches a certain level, then it's not feasible to even test your system at all of the operational states that it can reach. So how can you make sure that during operation, none of the emergent behaviors that are bad won't show up if now you're not even able to test your system at all of the operational tests? That effectively negates validation officially of your system. So yeah, they were blaming systems engineering. This is all systems engineering, right? So they came up with a solution. And I'll make clear, DARPA came up with a solution, and it was the meta design flow. So they started and they stood up the Adaptive Vehicle Make program. This was the portfolio, and it was a portfolio of 3 programs. It was Meta, IFAB, and Vehicle Forge. And all 3 programs were really related, and the work was executed in conjunction. If there was a Meta program, they would work and they would use IFAB and Vehicle Forge. Meta was more focused on the systems engineering and the method itself. IFAB was focused on the manufacturing aspect of it and how do you automate manufacturing of that system. And Vehicle Forge was a little bit more focused on the software tools and on crowdsourced design. And the purpose of DARPA, once they saw all these things, was to drastically transform systems engineering and to reduce the development time of complex systems 5-fold. Very bold claim, not mine, is theirs. So this is a picture, a very old picture of the Meta design flow. This was being proposed around 2010, 2011, so you get a reference frame. So don't expect anyone to understand what's going on there. I'll explain in more detail later, but I want to point out one important thing, and it's those red arrows that you see over there. Those arrows represent 3 very important prerequisites of the Meta design flow to even get started. And those are a formalized design language, which today we recognize as SysML and those kinds of things. Define system level requirements and concept. So all of your very early systems engineering products had to be defined beforehand. And then, and this is the very ugly one that we'll probably talk a lot about, a detailed component model library, already defined to very detailed levels. So these were not only descriptive models like model-based systems engineering models, they also involved computer-aided design drawings and models for detailed analysis. Like if it was a mechanical component, you needed to have the model to do finite element analysis and computational fluid dynamics. If you had a circuit, you had to be able to execute the circuit through an analysis. So these are very constraining requirements, but that's kind of what they had. So what's actually that Meta design flow? There's a picture there, a different view of it by one of the software developers that participated in the program. And it had 4 stages. So first and foremost, you would spend a lot of time up front focusing on your architecture. They proposed that a lot of the systems engineering effort to be shifted towards working on the architecture, optimizing the architecture for adaptability and to minimize complexity itself, and to focus on defining your interfaces as best as you could. Then once you did that, and remember, you needed to have your requirements and your concept ready, and you needed to have your component model database. So the next step after that was, from your component model database, start plugging in components into your architecture. So if you have an architecture component that's a radar, and you have 20 different radars that can match your specification, you would create different architecture alternatives that are different combination of all of your different components that are in your database. And then after that, you would take all of those architectures in a software tool and start running analysis on them. You would start with very low fidelity analysis, even just requirements-based checks, like this combination of components exceeds the weight of this subsystem, so they can't be together. And then you would continue to iterate, refining the fidelity of your models, and at the same time, reducing the number of alternatives. You would start getting alternatives that didn't pass your previous stage of analysis out of consideration until eventually you ended up with a reduced set of architectures that are now going into a trace study. Or potentially, if your analysis fidelity is high enough, you would execute this as the trace study and optimize on architecture. All right, so how can this be good for systems engineering, or what were they claiming that this could help in systems engineering, and my own observations of it? So first, you got all of the benefits of model-based systems engineering. So it's things like promoting modular open systems approach, promoting tightly bound, loosely coupled architectures, shifting systems engineering to earlier in the development process, increasing the level of abstraction, model-based verification, and you got faster requirement-based trace studies, all the normal things that model-based systems engineering can do. But on top of that, they were also proposing composing your system design from predefined components, and that's a very wild idea. That translates to removing component-level development from systems engineering at all. And they were arguing that and it's not for everything, right? A lot of people may already be thinking, well, that doesn't work for my system. Correct, that doesn't work for a lot of systems, but there may be other people thinking, well, yeah, of course that happens. We build our system from all commercial off-the-shelf parts. That's what they were addressing. Those are the kind of systems that they were addressing. How would they reduce the development time for complex systems? Their thought process was that you're shifting systems engineering to earlier, right? You're focusing on your architecture. You're making sure that your interfaces are as correct as possible. On top of that, you have an analysis tool, a software tool that is exercising all of your architecture through all of these layers of analysis, incremental layers of analysis with increasing fidelity. By the time you finish that, all of your inspection-based requirements would have been verified. That's what they mean by correct by construction. You already analyze that your requirements are met by doing the analysis on the architecture alternatives. And what they were arguing was that since you spent more time building a better architecture from the start, by the time you got to testing, you would have fewer surprises. And that's all. And that's where they wanted to save time. That was DARPA's argument. And eventually, if you do this enough times, since you're building all of this infrastructure, analysis infrastructure in your company, next time you want to do it, instead of starting from scratch, you just use your same models. Think about designing a car. Now you have all of your components in your component model database, and now you just create an architecture that's optimized for a different user base, and you just hit go. So basically, the meta design flow was intended to leverage model-based systems engineering and expand it. All right, so here's an example, and let's go with me. I have a couple of Venn diagrams of how these things may work, and these are not very detailed examples. It's just kind of an idea, right? So you start traditional trace study. Your entire component design space, think of this circle as anything that you can build. All of your components are there. Everything that exists, that doesn't, that you know and you don't even know. And then, how does a trace study go? Well, you get a bunch of SMEs and systems engineers, and you decide from that entire design space and everything that they know, they select a subset, right? And that's where the trace study alternatives come from. They just decide, oh, these are the alternatives we're going to consider, and that's where we're going to build the trace study. And then next step, you actually go through and make the trace study, and you select your architecture. Here's what we got. That's the best option out of the ones we considered. Well, what DARPA was proposing with the meta design flow to be different about this process was that, yeah, you start with the same design space, but now, instead of relying on your SMEs and your systems engineers to select your candidate architectures from their experience, you would have a component model library that already has in software component models that represent a subset of your design space, of course, because everything that hasn't been designed isn't there, but at least you have verifiable or verified components that are available in some fashion, and you have models of them. So that's already there. And instead of selecting by hand a subset of them to build your architecture, you will run analysis on them using your tool to then down select to the level where you can actually perform a more detailed trace study or to eventually do the optimization of the design yourself. And potentially, and this isn't going to always happen, but potentially by increasing the number of architecture that are being considered in the trade study at all, you would be more likely to not miss your optimum design architecture in the first place. So think about the idea where your SMEs select architectures to compare, but none of them are the best one, then you're not gonna find it. At least with the meta design flow, you make sure that within the components that you have in your library, which are probably all the components that you can buy in the first place, you can run analysis that will yield the optimum architecture, at least within that. So here's another example. This is where the return on investment comes into play. So let's say you're doing that, and you do it for the first time. This is the same that was on the right before. You're doing the trade study with the meta design flow. And then let's say you want to build the next generation of your system. You're going to do it again. Well, now you've gone through this process once. So now you have all of those available architectures that you had. But as time went by and as the development process itself continued, your component model database will increase. There will be new designs that get added to your library, and now you have a bigger design space that you're considering. And also by refining your tools, which if you remember is part of the process itself, continuously increasing the fidelity of the tools. Now the next time you're gonna do it and you're gonna run these analysis, you're not spending the same time developing your tools to run the analysis. You have them. They're more mature tools in the first place. You're using the same and other components. So now you can click a few buttons and it's gonna run faster. So your actual trade study runs faster with subsequent applications of this process. All right, so this is probably what most people here are thinking right now. This is such a great idea. Why isn't everyone doing it, right? That's what I thought. That's what most people who I explained this to think at first. Well, it wasn't that easy. So first, most people don't even know about this. And I would argue most people here didn't even know about the meta design flow in the first place and DARPA's approach. They didn't share this so much outside of the programs themselves. Second, those constraining prerequisites. It's not for everything. There's a lot of system development efforts that are not compatible at all with this approach, and this was never intended to be a one-size-fits-all silver bullet kind of approach. This was very specific for very tailored system development efforts that were already compatible with this approach that would have those component model databases that would use components that did not require top-down system development approaches that don't require requirements flow down from the top level down. Because once you get that into the mix, you can't have a component model database because nothing exists, right? And then the legitimate theoretical foundation. So there was one document, one very good document that explained the philosophical reasoning behind why all of this is supposed to work. But outside of that document, there wasn't really a lot of comparison to other systems engineering methodologies and how this falls in place compared to traditional systems engineering. So my problem, Anthony Millan here, or Anthony Millan 2 years ago as a master's student considering a project, it's kind of a story, right? So you got the meta design flow. It's proposing a solution to this complexity problem, right? Let's transform systems engineering. Let's make it better. Let's reduce development time. But, and also, it's a good idea. That was my mindset, right? It's a good idea. It has the potential to improve systems engineering for specific domains that are already compatible with it. But, as you can see above, there were some barriers to its broader implementation in industry. For someone to go and pick it up, they would need to first know about it in the first place. And then they had a methodology that was vaguely described, vaguely theoretically founded, and they would have to tailor their own systems engineering processes to try to do something with it. So, doing a literature review on it, I found that, if I could just tailor a systems engineering method, an end-to-end systems engineering method, to include this methodology in it, to include the meta design flow, then any systems engineer who wants to use this in their project, who already saw this as a great idea, as I did, and thought that it was compatible with their own project, could pick it up and just apply it, or just tailor my already tailored approach to their specific project. And that's what I decided to do, basically. And that's my research. So my portion of it is the methodology tailoring to incorporate the meta design flow, not the meta design flow itself. So I'm not claiming myself that this will reach 5-fold development time reduction. That was DARPA's idea. I agree that it can happen, but I didn't make that up. So what was my approach? It's 3 simple steps. So first, study the system development lifecycle of a project that is using the meta design flow. Second, study existing systems engineering methodologies, both traditional systems engineering and model-based systems engineering. Just compare them and compare them to the meta design flow, see if they're consistent or not. And then finally, just tailor one of them. Choose one and tailor one of them, following the INCOSE Handbook's Chapter 8 on tailoring processes, right? That's a very good tool, and following that guidance, basically, you use the system development lifecycle itself as a reference for what the modifications need to be, and then you can either modify your processes and your activities, create new processes, remove them, do whatever you want, as long as it's justified by the differences between your methodology that you're tailoring and your specific project, which was anything using the meta design flow. So that's what I did. And here to the right, you can see this was my depiction of what the meta design flow system development lifecycle stages were. And that's tracing from the system development lifecycle shown in the Systems Engineering Principles and Practice book by Kosikov and Company. So you would have a few differences, and 2 important things to notice here is that a lot of concept definition, advanced development, and engineering design, many of those activities were integrated, put together, and messed around by this meta design flow, and they would become this one big thing that is the meta design flow, which had processes, but they were not sequential. They were not sequential stages. They were things that were so iterative that you would have to do all of them over and over again, like 20 times, 50 times, however many times. And then the big part, the purple portion on top, as I mentioned, removing component level development out of systems engineering. Forget about your components. You're gonna get your component developers. They're gonna build you components, they're gonna give you your models, and you're gonna have your component model database, and you're just gonna use your components as the building blocks of your system. As a systems engineer, you care only about your architecture and using those components as Lego pieces to just plug them in and run analysis on them. Not for everything, but for wherever it works, seems like a great idea. All right, so I evaluated 14 different methodologies, systems engineering and model-based systems engineering. 8 of them were traditional systems engineering, 6 of them model-based systems engineering. And I had a few evaluation criteria. The most important to me was keeping in mind the goal of my research. Remember, my idea is that I want this to be used by more people. So I can't have a methodology that's already very similar to the meta design flow, because I can just say, yeah, how do you tailor this for the meta design flow? the meta design flow is it already. So it wouldn't clarify anything. It wouldn't extend the theory beyond the meta design flow. So all methodologies that were too focused on architecture and model-based systems engineering already, they're great. They're preaching the same story, but it's not good for the tailoring process because I'm not expanding anything. I wanted to care about, well, how do you do requirements now that you have the meta design flow? How does this affect testing? Does this affect operation at all? The other criteria was how compatible that methodology already is with the meta design flow. So I didn't want to have something that's so wildly different or structured in such a wildly different way that I would have entire processes that had nothing to do with the meta design flow. The other one is the relationship with the system development lifecycle. So think about things like agile or development life cycles that are tailored to specific projects and are so wildly different that now your methodology doesn't mesh with a proposed design flow that relies heavily on shifting the efforts of systems engineering to earlier development stages, right? Couldn't get something like that. And finally, it's flexibility for tailoring. So it needed to be a methodology that was defined deeply enough, and it's deeply enough in terms of the detail of the processes themselves, but at a level that is not implementation specific. And what do I mean by that? I was looking for process guidance that would tell you this is what you do. I wasn't looking for methodologies that went about and say, this is how you do it, right? Wanted to get what to do and change that for the meta design flow. So there were some runners up, 2 top contenders, and the first one was the Kosyakov Systems Engineering method from Systems Engineering Principles and Practice. I like that one a lot. So for those of you who don't know, that's a very cool systems engineering methodology that is very independent of the system development lifecycle. It has 4 stages, 4 processes that you continuously apply at all stages of your system development. It cares more about this is what you need to think about when you're doing systems engineering, right? And always think about these things, do them differently at each stage, and you're gonna get it done. Some pros of this: it had very good built-in flexibility for tailoring, and it was very independent from the system development lifecycle, which was good and very complete. Since it was independent, you could apply it to every system development stage, so it would go end to end. But from some cons was that its structure was very incompatible with the meta design flow. The meta design flow definition was very heavy on architecture and design, but from a physical perspective, so functional definition and requirements, they were not included in the meta design flow at all. So from a tailoring perspective, I would have to always go back and say, yeah, this is how you're doing requirements at this stage and the other one, because it was never addressed by the meta design flow. But then I would have a lot of detail to include for physical aspects of the system, because there was a lot of that in the meta design flow. So the other runner-up, sadly, is the object-oriented systems engineering method. I got some people who are very sad about this not being the one that I tailored, but there were reasons. So it's a very good approach. It's a model-based systems engineering approach, and it focuses on leveraging object-oriented concepts for model-based systems engineering. But it was, pros, it was very compatible with the meta design flow, and it would have been very easy to tailor. But kind of at the same time, those were also the cons. It had limited scope. It was so similar to the meta design flow that I could have written a few sentences and said, tailoring the object-oriented systems engineering method for the meta design flow is just changing a few words and that's it. So it's too similar. And that's where my research goal comes in. If I had done this, I wouldn't have really expanded the application of the meta design flow because I wasn't addressing a lot of the aspects that I wanted to get to, like requirements with the meta design flow, testing with the meta design flow, and how does a systems engineer in general can get guidance to do anything in a project, right? So who won, and people may have already known, was the ISO, IEC, IEEE a methodology from the INCOSE Systems Engineering Handbook, specifically the technical processes. And that's just because of the scope of what I'm considering a methodology. Those were the ones that were relevant. So it had a built-in method for tailoring, which is the tailoring process itself is Chapter 8. Its structure, since it's detailed, it has 14 different processes. So it was so detailed that it lent itself very well for tailoring, and how complete it was from end to end. Some cons, it was very dependent of the system development lifecycle, and while I wanted to avoid that, I had to accept that as part of my process because it was such a good match for tailoring. So this is what I decided to do, and this is my final tailored methodology. So hopefully those who are familiar with the INCOSE process can already see that a lot of it remained the same, and don't pay so much attention here. This is just a visual of how it looks as a V. But imagine here, one thing important that may be missing is the implementation process. It's nowhere to be found. All of that is component level development, and that's not a concern for the meta design flow. This is another view, a different view that goes into a little bit more detail in terms of what the actual meta design flow is, which is captured within the process called architecture definition and analysis. So if you recall, those 4 processes that I talked about, they're right there. Logical architecture design, spend a lot of time there, get that right, and then just iterate through defining the physical architecture. You get your analysis of alternatives, and you refine your analysis and go over and over. Eventually, you will get your architecture that's already optimized, and flesh that out and start integration, start buying your components. So the bulk of my research was actually this part right here. It was discussing how the tailoring itself was done and what the guidance, the specific guidance is for a systems engineer who wants to use the meta design flow in their project and wants an end-to-end systems engineering methodology that allows them to see how does everything change now that I want to use this meta design flow and do my systems engineering with it. How does everything else change? And those are the blue processes right there. Those blue boxes, those are all of the processes that were modified in my methodology. And there's a lot of discussion in my document about how, for example, how those requirements, all of those requirements definition processes change. There's special considerations. Remember, one of the prerequisites of the meta design flow itself is to have your requirements already defined, but requirements definition and analysis is an iterative process throughout the development lifecycle. A lot of systems engineers are used to that. So now, if you want to use the meta design flow, you need to be a little bit more strict earlier about stakeholder buy-in to your requirements. You need a more mature set of requirements going into your design phase. That's one consideration. It sounds ugly and very bad, but it's something to consider. You will need to be more strict about your requirements if you want to execute the entirety of your architecture development and design at the same time using software. Think about it. You need very good requirements because your first analysis are going to be requirements-based. Another thing, how does testing change? In that portion, I talk a lot about how do you take into account the fact that you now have very mature analysis tools and the temptation to use those for verification. Now, you have these analysis and you can just go ahead and say, well, yeah, I just ran analysis on my architecture, so all of my requirements are verified. Well, be careful. Now, if DARPA's vision comes true, and now you start testing your system and you reduce the number of retests that you need to do because of failures, consider dedicating a little bit more of your budget for testing, specifically for the purpose of model validation. If all of your development is going to rely on those models and the design of those models, test a little bit more just to validate those models. And most of the discussion is really on the meta design flow and how things change, how the iterations themselves drive the development process and the limitations of such an approach, because even though it's iterative, it's not iterative always. One scenario that I discuss a lot is, imagine that there's a requirements change later on in your process, and you had already run through your optimization process. If there's a requirements change, then you have to start over. Think about that. You have to go back to the drawing board and build your very first architectures. Now you have software that's going to help you do that. That's what DARPA wanted. But take into account that that's where the requirements buy-in comes in. Your sponsors, your customers, they're going to have to pay for you to run through the entire architecture development and design process again if they want to change a requirement. So those were some special interest topics that I discussed in the paper. And all the gray ones, I didn't really see a need to change them. They're more specific about what you do after your system is in operation. So there really isn't a lot to change. Eventually, when things become real, it's just real systems engineering, and you have to deal with it accordingly. So last portion of my research was, how do I make sure that I didn't mess up and just made up something crazy, right? This is the validation. So I decided to use both quantitative and qualitative approaches. So the qualitative approach, I did a peer review of my methodology with some experts. Hopefully at least one of those names a lot of people recognize. Sanford Friedenthal was gracious enough to support me and take a look at my methodology and give me comments. And the other one was Clyde Smithson. He's from APL, and he was the systems architecting subject matter expert who looked at my methodology. All of their comments, and they were very good comments, and what you're seeing here is a result of those comments. Those comments were incorporated iteratively in the development of the methodology itself. And then the quantitative approach, if people may remember from around here, I ran a survey of the systems engineering community, or at least a very, very reduced subset of the systems engineering community. I ended up getting only 22 responses, so I can't claim that there's sufficient validation of the methodology based on that, but there were some good results, and these are the results right here. So I had 4 categories of questions that I was asking people. They addressed completeness, conformity, feasibility, and adaptability. And there were some very good comments that I discussed in my paper, particularly for conformity and adaptability. People loved it. Everyone was saying, oh, this is great in terms of that. But you can notice maybe that completeness got the worst grades out of everything. It was mostly positive, but still, it's the highest grades for neutral and the highest grades for negative, lowest grade for positive. So what happened there? Well, there were recurring themes in the comments that people were telling me. So first, the apparent exclusion of functional analysis in the methodology. If you may remember, it wasn't mentioned at that high level description of the methodology, functional analysis. Does that mean that it's not there? Well, that's not the case. It is there. Sadly, to me, who had to go through this, the ISO, IEC, IEEE process itself doesn't include functional analysis at the top level. It's actually addressed in activities within requirements definition processes. So it's there, it's just not visible at the higher level. A lot of people didn't like that. Got a lot of comments saying, oh, you can't forget about functional analysis, what are you doing? Yeah, well, I didn't, or if I did, INCOSE did too. So second one was apparent lack of iteration between processes, and I get that. The meta design flow itself is an iteration, and one of the diagrams really emphasized that. In the visual representations of the methodology that I shared, the iteration wasn't emphasized, and that's my fault, but there's inherent iteration loops across the different processes. Even though this methodology is, it conforms very strongly to the system development lifecycle, each of the processes, you can always go back to the previous process and iterate again. So that was my bad for not representing it, but it's there. And then the last one, and this is a real technical challenge for the acceptance of this approach in industry is that the availability and the fidelity of that component model library that this process requires may not be there today. And that's very true, and I discuss about this limitation in my paper. And yeah, it's a challenge, and I accept it, but as you may see later, that's one of the challenges that I would like to explore, because I've heard both ways. Some people think that it's there, some people think that it's not, so I would personally like to find out. So conclusions of my master's thesis research. First of all, system complexity is still a challenge for systems engineering and will continue to be probably forever until we find a one-size-fits-all solution, and I don't think we even want to. That's why we exist, systems engineers, because it is continuously a challenge. The meta design flow that DARPA proposed has the potential to help for very specific domains that are already compatible with it, not for everything, of course, and it leverages model-based systems engineering. So even though it has a lot of potential, there are a lot of limitations to this approach that need to be understood, and a lot of special considerations that any systems engineer who wants to incorporate it to their projects needs to take into account. And I realized that, and that's why I wrote the tailored methodology to help. So that's why I want to publish this, this product for the benefit of the systems engineering community and anyone who finds this to be very useful and wants to use it. And overall, even though I didn't get a lot of participation, the comments about the methodology were very positive, so that at least hints that there could be acceptance in the community. So then, after that, after I finished everything, or actually before I finished everything, this part came up. So I was able to present a specific potential application of this methodology to one domain, which is healthcare, at the 2018 Systems Engineering in Healthcare Conference. And the topic was improving operating room design through innovative systems engineering methodology. It was all this same presentation, the systems engineering methodology, and then I had a little bit of comments about how can this be applied to operating room design, and how did this even come to be? So first, this was very early on identified by my research team as a potential application. But why? What are the reasons? Well, there's two main reasons. First, this problem is very compatible with the meta design flow. Remember, meta design flow isn't for everything, but it may be for operating room design. Why? Well, first of all, operating room design is not a top-down systems engineering approach. Or have you ever heard that someone goes in and builds an architecture for an operating room and then flows down top-level requirements and gives a specification to the medical device companies to build that? No, that's not the case. The medical device companies, they go and they build their equipment. They make them compatible with other things, and then they will sell those components or already subsystems or even systems in their own merit to the hospitals, and someone at the hospital, like a group of doctors, they decide what to buy and integrate into a federation of systems those components. So that's what the meta design flow is saying. Do you think that you can't get all of those medical devices as models in a component model database and build an architecture optimized for the needs of the physician and the patients, and then just plug and play optimization tools that run analysis on those external interfaces, which, by the way, are probably low fidelity at the external interface level? I think is very compatible. And the second, that the meta design flow itself would provide very specific benefits for operating room design. For example, shifting the focus to the architecture level, which isn't happening, already provides benefits. Reducing the system complexity. If you optimize the architecture of an operating room, you avoid things like getting tangled up in cables and things like that from the architecture level. I know the medical device companies, they try to do that already at the component level, but what if you had the architecture itself optimized? So there's a lot of benefits there. And they agreed, actually. I got a lot of good feedback, even from the medical device companies themselves. They were interested in following these approaches, and probably they were interested in selling an entire operating room to a hospital now by following this approach, or making sure that only their devices are compatible within the architecture. But it was good discussion. And this is my research, my PhD research proposal. So this is my idea of how to expand this research outside of what I did in my master's. So I proposed 4 areas of expansion to this research. Starting at the bottom, I have the practical application. Of course, my validation wasn't very real because I couldn't test this in a semester in a project. So I'm proposing at least a few case studies where you could get a project, a funded research project, and try to do this and see how far you can get. And whether it's actually feasible. That's really the second part. How do modern model-based systems engineering tools enable this? Remember, I said this was done 2010, 2011. Well, we're in 2019 now. Model-based systems engineering tools have come a long way. There's Model Center and tools like that that are really focused on integration between model-based systems engineering and analytical tools. DARPA spent most of their money trying to develop software tools themselves to be able to do this. So now maybe we don't need to do so. The next one, systems engineering theory. I noticed later, after I finished my research, that I really focused a lot on that very first application of the meta design flow. And my discussion is really, it comes off as being very restrictive. Even as I was explaining it here, most of my discussion was, yeah, this is what you need to take into account, but this is bad about the meta design flow. Now you need to do requirements in a way that's not very natural. You need to be careful with testing, but I didn't really address the evolution of the methodology itself for subsequent applications of the meta design flow. That Venn diagram where I was talking about the increased return of investment, I didn't discuss that very much in my paper, so that would be something I would like to explore. And finally, there was a lot of discussion and feedback about, well, how does this meta design flow, which seems like a great idea, how does it work in a project that's trying to do agile? How does optimization work within the framework? If you're trying to do trade studies, wouldn't you want to do just automated optimization and stuff like that? So I would like to explore those topics in my PhD research. And then finally, I want to say thank you to everyone. If anyone's interested in discussing further and has some potential application ideas to discuss, those are my email accounts. And then special thanks to everyone who's helped me through this process. Max Kronover, my master's thesis advisor, my thesis board, Mike Pafford, former president of this chapter, Kathy Rubin and Larry Strausser, Sandy Friedenthal, and Clyde Smithson, my peer reviewers, and then my current PhD advisors, Mike Borky and John Labadie, and finally, my family and my friends who have been very helpful. So with the few minutes we have, questions?
We have time for a few questions.
Thank you.
Thank you very much for a fantastic talk. But yeah, in the long run, we've had some lecturers here, Bo Gorley, looking at maintenance, logistics, and upgrades. So when you're talking about a system, and if the mission and ConOps are similar, but there's a heck of a big difference in architecture and a lot of real capabilities in the upgrades, like the Northrop Grumman E2C, Grumman, and then to the E2D. After 2002, 3, took them a long time. So how do you handle that? In the feedback process and iterations and so on. Applying some of the similar techniques.
Yeah, so you're talking about for updates of the system that have significant architecture changes. How do you go about the iteration of this process? And I will go a little bit further back, and as part of this fundamental theory behind this meta design flow. Arguably, at first, the very first thing you did is that you built an adaptable architecture. So The idea is that if you use this process, you would have an architecture that itself is better and it's easier for you to do upgrades because you've built the architecture in such a way that's adaptable. So that's one of the focuses. That's what they were proposing. So in terms of actually doing it, once you do that and your architecture is adaptable, remember now you have a model of your architecture and models of your system that are already defined. So if you want to go and make an upgrade, you can do minimal changes to your architecture level model and then run the iterations again if you wanted to do that. Yeah, so that's a very good point, and that's one of the challenges of this process. Remember that the requirements and the concept level definition were inputs into the meta design flow. So one of the shortcomings probably of this process is that if you build your architecture for a specific mission, for example, and it's not flexible enough to address mission changes or the specific mission changes, you may need to go back to the drawing board. And if that may be the case with your system, just consider not using an approach such as this one.
We have another question.
Just one more. Loved it, by the way.
Thank you.
Very good. Thank you for using the diagram. I
Sure.
appreciate that. But the aspect, I teach the 15288.
Yep.
And the aspect of you just have to help me with that, getting rid of implementation, because the whole idea of getting to the point of design is designing those components. Now, I noticed
Yeah.
you kind of got rid of that or
Yeah.
modified that
Yeah, so I'll
because
explain.
it's now all model-based and you're bringing in your components. But I guess my question, if you don't mind, if you find your components aren't enough and you need something, what happens then? I mean, so that's
Yeah.
what gets me is like,
Yeah, so I'll say-
it's a wonderful idea if all the components are there, but
I'll say
if you're looking for optimization, you may not find all the components are there. Right?
So thank you for the question, but I'll say I've thought about that because
Yeah.
many smart people have asked me about that specific scenario, and I've developed it, even though I didn't discuss it because it's kind of a convoluted idea. So now think about it. Immerse yourself in the idea that you already have all of these tools in place. Right? You have a system-level architecture, a logical architecture that is blanks that you can plug in your components. You have a company and you need a very specialized component, a new component to substitute your component that didn't meet the expectations.
Right.
Well, you have model-based systems engineering to help you with that. Now, in your company, you can have a design team at the component level. It's not considered systems engineering by the standards of the meta design flow, but now you have your architecture, you have all of the rest of your components. So now you have like a system level, like prototype, virtual prototype to do the development of your system. You have all of your
that's
external
brilliant. Yeah.
interfaces already defined for your component. That makes it very easy for a design
does.
team to go and optimize a component and plug it in.
Excellent. Okay, thank you.
Sure, thank you.
Thank you.
Very interesting presentation, thank you. And just a quick question about verification. In your beginning, you said with the independent V&V that as systems get more complex, that was the challenge. You couldn't go down through every path and verify and test everything. So I was a little bit surprised when you came up with your final design process that the verification block seemed to be the original. So how did that evolve or morph?
So validation was the same. Verification I hadn't modified. And I didn't go through all of the explanations, but I'll just bring it up again. So verification is blue, it's modified, validation is gray. And the distinction I'm making there is that validation addresses more the highest level stakeholder needs, right? You just make sure that it actually does what it needs to do, and there's not gonna be any changes to that. You do that through testing, you really make sure that it's through operation and actually exercising your system, it does what it needs to do. But verification, there's a lot of discussion in my document about how verification can change. And DARPA's idea was, as I mentioned, that because you've been doing more analysis, and analysis is an integral part, even more so than normal, of your development process, and there's an extra rigor that is necessary in order to do that automatically, which is what this idea is proposing, that you've already done a lot of requirements-based analysis, and that's part of your verification. In addition to that, there's an extra layer of testing that is needed to now verify and now validate your models themselves as part of the additional verification of your design process. So does that answer your question, or is there still more? All right, thank you.
Yes, thank you for the presentation. You're talking to the right crowd with ISO 15288.
I hope so.
I was very comfortable, as you referenced 15288 and the tailoring and so on. But when you got to the combination word, I kind of looked up and said, I haven't heard that before. And my question is this an extension of tailoring, or what are you doing here? Why are you combining? Is it to streamline your flow?
All right.
Okay.
So you're talking about combining different processes.
Yeah, it's right there in the chart. Yeah.
So the reason why I did that is that the meta design flow itself proposes combining these processes as they are defined in 15288. So it's really, I would argue that really all systems engineering methodologies are the same. It's just explained in a different way. In the end, you're going to do the same things, but the way they define this, there's integrated architecture development with design, with trade studies, and you just iterate through. You just put it into a software and just run it. So I wanted to convey the idea that instead of them being separate processes, all of the activities are there actually. So all of the activities from these different processes are there. They just interact with each other in an iterative way that I wouldn't feel comfortable saying that they're different processes. They're just one big process, and it's a very big process, this architecture definition and analysis. It's a very big process that actually does all of those things. Architecture definition, it does design, it does analysis, but you just do it all together through the same software tools. So I wanted to incorporate those into just one process, because from the definition of process, input, activities, output, this is what made sense to me. You got inputs, your integrated modeling environment, you got your system requirements and your concept. Those are your inputs. You just crank the machine of the meta design flow and you get your architecture. And that's the distinction I wanted to make.
Thank you. Just one comment. The various paragraphs of ISO 15288 talk about what's the purpose of a particular task like maintenance or operations, and then it lists outcomes.
Yeah.
And so I understand the iteration thing, because we all know that that's a very specific process that we have to include. But are we de-emphasizing those individual outcomes for those various things?
So I would leave that maybe in a sense. There's some.
No, I'm not making a pointed question. I'm just curious.
No, I'll just say there's some de-emphasizing of those outcomes, those outputs that are intermediate. But in reference to this methodology itself, those inputs and outputs are internal to the process. So now instead of them being a separate product, so think about it now. You don't necessarily need your architecture to be a PowerPoint document by itself. You have model-based systems engineering, you have your architecture there in your tool. But now your architecture doesn't matter so much because you're filling it up with your components already. So your actual product is not the abstract logical architecture, it's your physical architecture that went through the optimization. So there are some of those inputs and outputs, those documents and things that are internal to the process instead of external, but they're still there. And they could be generated and shared with stakeholders if they want to, which they will most likely want to see them.
Thank you.
Thank you.
It occurs to me that there may be a nice marriage in your central block there on architecture definition and analysis for combining it with Scrum of Scrum's software development for the actual operating software of the system, and doing the development of the software and changes in the software as you do the design changes and so on.
Yeah, no, that's true, and that's a good segue to other comments I received. If you remember, I discussed that I would like to explore more the relationship between Agile and this methodology. And at first, I got comments that these approaches were not very compatible, and that idea came from the concept of this approach being very heavy on early on system development, systems engineering effort for architecture development. And well, Agile and Scrum, they're all about continuous delivery of products, right? Those seem opposite. But the more I've talked about this idea with the model-based systems engineering community specifically, most people keep telling me, oh yeah, model-based systems engineering is great for Agile, because now you have all of these models that are your specification, and you just give that specification to the software people, and they automatically generate code. So I would like to explore that in my research.
And that would also allow for the limitations of software to feed back into the component design.
Yeah, that's absolutely true. Thank you. That was the last.
Okay. First and foremost, a big round of applause for Anthony.
Thank you.
Thank you very much for a really good talk.